Okay, so the first mode of chromatography, of liquid chromatography, that we'll talk about in our discussion of partition chromatography is normal phase liquid chromatography, or NPLC. All right, normal phase liquid chromatography. So here is our solid support particle. There are silanols here, so let's assume this is silica, and then here's that. And we have clicked onto this thing some chlorosilane. So here's R primes, and here's an R. And the idea behind normal phase liquid chromatography is that the R group is relatively polar. So here's a couple examples of what would make a polar R group. So you generally have a couple of carbons of tether to kind of put this thing out into the solution environment out here. So a couple of carbon groups, and then something like that cyano group. So a stationary phase like this is often called a cyano stationary phase. We get similar functionality when we put amines out there, and these are often called amino columns. Or you get these diol functionalities. Things like, yeah, here we go, OH and OH. You get these diols, diol columns. Okay, so we talked about the thing that makes these things different, one from the other, is the composition of the stationary phase. Here we go. We've got we've set a landscape for composition of stationary phase and normal phase. And then what makes a solvent, or a mobile phase rather, strong versus weak. And so the way I like to think about this is in the context of gradient elution, although there's no requirement that you do gradient elution. You can do all of these isocratic. But let's think about this in the context of gradient elution. So we talked about gradient elution. We said that as time progresses, what you're doing is you're changing the strength, so the mobile phase strength. There we go, mobile phase strength as time goes on. We've described this in the past in terms of percent B. Let's just remind ourselves what that means. It would be sort of if you had a binary pump that can pump two different solvents, it would have the option of taking in solvent A or solvent B and putting out some mixture of that to the column. And a really basic gradient to do over time would be something like a straightforward linear gradient that looks something like that, right? So the mobile phase strength increases over time, or the percent B, the amount of solvent B that's being added into your flow here, would increase over time. So for normal phase liquid chromatography, the concept of mobile phase strength is synonymous with talking about polarity, right? So what we would say is that at the start here, we'd have a pretty weak mobile phase, and that would be a mobile phase of low polarity. Why is it weak if it's low polarity? Well, that's because the stationary phase is going to be relatively high polarity based on these functional groups. And so if your solvent is low polarity, it's going to compete very poorly with solution in that environment, right? And so it'll be weak. It won't do a good job of competing. Whereas we're growing as percent B increases to higher polarity. It's competing as time goes on, polarity. It's increasing as time goes on in polarity, and increasing its ability to compete for solvation with that R group. Okay, so let's talk about what we do to start with a low polarity and get to a high polarity. We have to think about how we choose a mobile phase for a system like this. So there are essentially two key requirements that a mobile phase kind of has to meet, especially if you're in a gradient elution system like this. So here's what they are. So we need both A and B to be miscible. In other words, they need to be able to dissolve in each other, because if they don't, then as we add %B in, we're not getting some nice linear gradient here. We're getting oil and water, right? We're getting droplets of one in a dispersed phase of the other, so that's no good. And the other thing they need to be is they both need to be compatible with whatever detector you're using. So we've talked about detectors and detection modes in the past. A good example here would be like ESI, right? So if we're doing ESI, the solvent needs to be polar enough that things are ionized in solution, or you're not getting any ions to go into your mass spectrometer. And so that generally means aqueous solvents. Here's the example we're going to use here because I think it's by far the most common. So let's assume UV absorbance detection. In that case, what we're looking for in these solvents in A and B to be compatible with UV absorbance detection is a low degree of absorbance from our solvents, right? If we have high solvent absorbance, we're going to miss the small change in absorbance that comes when there's analyte in there. And for UV absorbance, that generally means few or no double bonds, few or no pi character to the solvents. So let's look at some common solvents A and B for normal phase. These would be, so let's call this common normal phase liquid chromatography mobile phases. And so very common for A would be, saturated hydrocarbon, something that is very nonpolar, has a pretty good solvation capacity for nonpolar things. So this would be long saturated hydrocarbons. So heptanes or decanes are really common for this kind of application. As we're increasing %B, we're trying to get more polar. So let's think about organic solvents that are going to have some polar character. They need to be miscible with these highly nonpolar solvents, right? So it's a tricky requirement, and we will certainly not get to a point where something is as polar as H2O because those will never be miscible with heptane or decane. And so what's really common here are ethers. Really common one is methyl tert butyl ether, or MTBE. It is often abbreviated in the literature. All right, so we've talked about composition of the stationary phase. We've talked about what makes these solvents stronger or weaker, right? It's a matter of polarity. So the next question is retention order. That's what I said was the third factor in how these things differ. And so in this case, this produces the same or similar retention order as the classic SVET style adsorption chromatography. Right, it's going to do the least polar things. Will elute first, and the most polar things will elute last. In other words, these will have low retention factors, and these will have high, lowercase k, retention factors. And that's not surprising, right? We have a polar stationary phase, so things that are polar should want to stay on that stationary phase. They should move the slowest. But it does beg an important question, which is why do this at all, right? If we already have um, adsorption chromatography that can give us this kind of retention order, what are the advantages here? So there's a couple. Um, we can tune the stationary phase chemistry. We can't do that with silica. With silica, we get a really high density of hydroxyls at the surface, and we get a lot of high energy hydrogen bonding that's going to hold on to stuff really tightly. The ability to tune uh, the functional groups that we see at the surface, what this is essentially saying is that we can fine tune the selectivity factor, which we've talked about previously in the semester. This was factor alpha, right? This is the ratio of um, uh, retention factors, basically. So the ability to fine tune that surface chemistry, which we cannot do with silica, which just gives us hydroxyls, is a huge benefit. The other thing, the kind of the theme that I've hit on adsorption chromatography the whole time, is that we can reduce. Let's say that we're reducing the number of functional groups this way, the number of binding groups on the stationary phase. Right? What does that mean? It's that 25 to 50% yield I was talking about. Right? That low yield means that we have a lot less sites of binding. They tend to be binding of lower energy as well, and so the net result here is lower overall K values. As a reminder, I feel like I've said this a lot lately, but as a reminder, chromatography, right? We said it roughly stops being useful once your K factor is, or your retention factor, your K value is higher than about 15. We lose retention and we lose peak efficiency. And those are the two key things that kind of give us what we are looking for out of these separations. So by reducing these overall K values, by reducing the number of functional groups and essentially making them lower energy interactions, we get a benefit over adsorption chromatography by using these bonded phases in normal phase liquid chromatography. One challenge we should talk about. So here we go. So one challenge to normal phase liquid chromatography is the ability to work with, to separate analytes that are small molecules in general, and we'll say especially polar ones, especially small polar molecules. There's a couple reasons for this. Small molecules don't have a lot of steric hindrance to get down to the surface, the underivatized surface, right? So if we get 25 to 50% yield, I'm talking about the other 75 to 50%, right? So the underivatized silanols, they're going to cause adsorption, which is the thing we're trying to avoid here, right? That's going to give skewed or asymmetrical peak shapes, and overall it's going to drive up K values, which means longer analysis, potentially with worse performance. Okay, so last note on normal phase liquid chromatography is to say that NPLC accounts for on the order of about 10% of applications of HPLC. So about 10% of HPLC is going to fall into this normal phase liquid chromatography regime. And the next video we're going to look at is going to talk about reverse phase liquid chromatography, which is going to pick up a lot of that slack.